All right, let's get started. The first speaker of today's session is Colin DeGraf, and he's going to tell us about black hole mergers.
Yes, okay. Hi, everyone. Great to be back every year. Really nice having a conference like this that you get to come back to and have a lot of people that you know and new people every year, so thank you all for coming as well. So I'm going to kick off today's sessions, which are on black holes and simulations, by talking about black holes in simulations. So I'm going to mainly focus on, well, sort of mergers. I will motivate in the beginning and come back to at the end about mergers. The whole middle part will be, which is the bulk of it, will actually be about the sort of process of the black holes approaching each other until they merge. So a lot of this work is stuff done by Nyanyi Chen and Yuying Ni, and I also want to point out a whole bunch of undergraduates who were involved at different aspects of this. All of these undergraduates working on the merger part, not the middle part about the in-spiral bit, but have done a lot of work. That's really great. So, I don't think I need to motivate why we should care about black hole mergers, but just really quickly, I mean, they affect black hole growth. Black holes evolve with their host galaxies, and really understanding how galaxies evolve does require understanding of black hole contributions as well. And simulations represent a really good way to study this, right? If we're wanting to look at black hole mergers, zoom-in simulations are good. Individual black hole merger simulations are good, but if you want statistics, cosmological simulations is a really good way to go, and so that's what I'm going to focus on here. But a lot of cosmological simulations don't model mergers very well. Black hole mergers. So one of the things which is becoming progressively less common, which is a good thing, is what was very common in a lot of cosmological simulations is trying to model the black hole dynamics is tricky. And so the easier thing is just at every time step, move the black hole towards the potential minimum of the galaxy, which is inexpensive and easy, but also means that the motion of the black hole is completely not physical. And so you have black holes, when two galaxies merge, a black hole from the outskirts just artificially moves towards the center, and the mergers happen too fast. So, for example, Marta Voluntari had a paper looking at estimating how long it should take for a black hole to migrate from the outskirts of the galaxy to the inner part. You don't need to worry about all the details, but if you just look here, this is an analytic estimate for the dynamical friction-based infall time. And as you can see, it's really long. So the actual time it should take before these mergers happen should be a lot longer than a lot of these simulations do. And so then this is something some of the undergrads I had mentioned had worked on. So this plot's from Illustris, but we've looked at similar things with other simulations. And what you can see is this red curve is the rate at which gravitational wave signals should reach the Earth, how many per year, based on Illustris. And then here is what happens if you impose a dynamical friction infall time. Now, to be clear, this is doing something similar to this. Calculate an estimate for the dynamical friction time, and then impose that in post-process. So what you see is this dramatically decreases the rate at which mergers would be occurring. But we really need to do better than that, because you could also compare with host galaxies. So this is the same set of undergrads working, and what you can see is this is using the Illustris simulation, and the gray dots are galaxies hosting a black hole merger at redshift 0.9. But if you delay all of these mergers using these dynamical friction times, then instead you would get these blue dots, and these gray open circles are the higher redshift time when Illustris originally merged them. So you can see Illustris was merging black holes tending to be high redshift and a bit more overmassive compared to the local relation, whereas if you delay the merger, they actually end up being a bit undermassive. So there's a lot of reason to try and really incorporate this dynamical friction directly into simulation. And so what I'm going to talk about is the Astrid simulations, which do exactly that. So I'm not going to go through details of how the simulation works. If you're curious, talk to me. I've also put some different references so you can look at a lot more details if you'd like. But ASTRID's a very large volume box. The gadget SPH code. I'm just going to mention a couple things about the black hole model since that's what I'm talking about. It uses Bondi-Hoyle-Littleton accretion. There's thermal and kinetic modes of feedback. Neither of those are really the focus of what I'm talking about. But because I'm talking about black hole mergers, one note to make. In this simulation, they merge when you have a pair of black holes that are less than 3 moving H inverse kiloparsecs away from each other, and when they're gravitationally bound. So the gravitationally bound criteria is really important because you will have many paracenter passes, as we'll see shortly. The other thing that ASTRID does differently from a lot of simulations is the seed model for black holes. And so it's actually a range of seed masses, and it's a lower mass than is often used in these large cosmological simulations. So the seed mass is based on a power law distribution. And then, because I don't have time to discuss any of the details, there is a dynamical friction model. It follows similar methods to Michael Tremel's models, and there's whole comparisons to exactly Michael's models as well. But this allows us to follow the black hole dynamics. So that's all I'm going to say about how the simulations work so I can get into the more interesting results. So this is the black hole mass function in ASTRID in red and in TNG 300 in blue. And so you can see, and at many different digits. But you can see pretty good agreement, but in particular you can notice this difference. So this spike right here, that's the seed mass for TNG. On the other hand, when you look at the seeding area for ASTRID, you don't have a spike, you have a essentially nearly perfect power law. That's the power law distribution for the seed. So we're able to push to lower mass black holes, and that's really helpful, for instance, when making predictions for LISA, which I'll get to at the very end. So given this large volume simulation, we're able to model the dynamics well. So now I want to take a look. So here are a couple of different examples. So it's centered on the black hole in red, and then so each row here is a different black hole pair that merges. And so you can see this trajectory that is coming in, and it really has many paracenter passages before it will finally merge. Or in some cases, some don't merge till the end of the simulation, as you would expect. But we can then investigate what happens as these black hole pairs are approaching each other. So, just to show you the importance of dynamical friction, this is a high redshift merger, and the real key just to look at here is this color scheme that extends out for quite a ways. That's if you don't include dynamical friction. Whereas these other colors include different dynamical friction prescriptions, and so it takes about, depending on which prescription here, it's taking about 100 mega years to merge from the starting point when we're tracking it there. Whereas it takes about an extra 150 mega years after that if you don't include dynamical friction. In the case of high redshift, we can see that the dynamical friction from the stars and from the gas are both significant and sufficient individually. If we look at low redshift, however, what you see is this one that never merges. That's no dynamical friction. The green one here has dynamical friction from gas but not stars, and also does not merge. So once you get to lower redshift, the stellar density is more important, so you really need the dynamical friction from stars. But again, we're getting them to merge using dynamical friction to bring this. So we can look at sort of examples of what's happening to individual merging pairs. Again, this is comparing no dynamical friction in blue to dynamical friction in red. And you can see the dynamical friction very quickly brings the black hole close, secondary black hole close to the primary. This is the separation of the pair. And so this allows the black holes to, in a physically realistic way, be brought into the center of the galaxy. So we can look at statistics for these pairs of black holes. So in this case, a black hole pair, first off, we're limiting ourselves to only consider black holes above 10 to the 7. That is to look at the things that are best resolved and not have to be concerned with parameters for the dynamical mass of the black hole. So we're just looking at the massive pairs in this case, and we're going to define a black hole pair simply as when you have two black holes less than 30 kiloparsecs away from each other. But we're then going to subdivide that up, so a dual AGN is simply when both of those members of the pair are above 10 to the 43, and an offset will be when one of them is above 10 to the 43 and the other is below. So do note, offset here doesn't require an active AGN offset from the center of the galaxy. If you have a pair and one of them is very close to the center of the galaxy and is the active one, it doesn't visibly look offset, but we're still defining it as offset for the sake of this analysis. So if we look here, this solid pink line, that's the fraction of black holes that form dual AGN. And so you can see it's not particularly redshift dependent. Once you're below redshift 4, sort of is increasing from 2 to 3%. If you compare that to the offset case, where only one of the two is active, it's drastically evolving with redshift. That's partly based on having more minor mergers at late times that allow them feast to form. So I just want to point out an observational comparison that came out this year. So this is using Cosmos Web, and so you can see this is the Astrid prediction, and then these dots are the Cosmos Web measurements. So they are doing a very good job of matching. So I now want to take a look at what happens in one of these mergers. So this is an example of a dual AGN. And so if you look here, this is black hole masses. So you have one large mass and one small mass black hole. But the lower mass black hole actually overtakes the initially larger one simply because it has a higher gas density surrounding it. So the idea here is you have first paracenter, second paracenter, and roughly around second paracenter passage is when the secondary black hole's accretion rate overtakes the primary, and then a bit later the mass overtakes it. So this is relatively common for the dual AGN in the simulation. So the offset is a little bit more to look at. So I'm going to do this in parts. So to begin with, if you take a look at the black hole masses here, this is an offset AGN. So at redshift 3, only one of them is luminous. But you can see their initial masses are actually very close. In fact, much closer than the dual AGN. So this offset AGN does not rely on it having been a minor merger. It happens with major mergers as well. So it starts out fairly comparable mass. We then go past the first paracenter passage, and what you see is one black hole gas supply increases substantially. So that is then, the primary black hole is then able to accrete quite efficiently. But if we move slightly past that, at second paracenter, you can see the secondary black hole loses the vast majority of its gas supply. So this is stripping of the secondary black hole. And then, if we continue it, you see that once that secondary has been stripped, it really doesn't grow, and the merger is stalled. Because we've stripped it of gas and most of the stars, it really can't be driven into the center to finally merge. So we can track these and see what happens. So this plot takes a second to explain, but this is selecting all of the dual AGN at redshift 3, and then, looking at them as the simulation evolves forward in time. So the y-axis is showing the percentage of those which are duals, offsets, or having merged. So right at redshift 3, it's 100% the greenish color. So all of them are dual because we've selected just the dual AGN. But as we evolve that with time, you can see very quickly a very large percentage of them merge together. So when you have these dual AGN, fairly quickly they end up merging. You can also see there's a decent percentage that actually remain as dual. And a very small percentage become offset. So when you have a dual AGN, they tend to merge relatively quickly. If they don't merge, it tends to stay as a dual. But We can also look at what these look like before redshift 3. So again, we're selecting them at redshift 3. So if we extend this out to look at what was going on before redshift 3, you can see up here, this is before they formed a pair. So they were more than 30 kiloparsecs apart. And so if you go back far enough, most of them haven't approached each other. But you can see the ones that are dual at redshift 3 became dual fairly quickly, and it's pretty uncommon to be offset. So the ones that are both active at redshift 3, it's unlikely that they spent much time with one of them active but the other quiescent at an earlier time. However, you may notice this says same galaxy dual. Now remember, dual AGN here is based on only a distance cup. So you can have two black holes in different galaxies. When the galaxies approach each other, they could be within 30 kiloparsecs. So we can look at what happens there. So here, this is, again, selecting at redshift 3, dual AGN, but where those AGN are still in different galaxies. And so, again, you see they used to be far apart, but now you see they get a decent percentage becomes far apart again. So this is because you have these two different galaxies, they pass by each other, they then separate to become more than 30 kiloparsecs, but then tend to fall back in. As you can see, the percentage that stay far away from each other is very low. So again, we have a lot that merge. We have a decent percentage of offsets and a decent percentage of dual. So when they're coming from different galaxies, there's a much higher chance that they don't end up merging. We can then take a look at what's going on with offsets. So this is the exact same idea, except we're selecting all the offset AGN at redshift 3. And you can see a similar idea, which is if it was offset before. But you see, unlike the dual, the offsets don't merge. I mean, very few do. There's this little bit that will end up merging. But like I was saying, the offset AGN tends to stall, and we don't end up getting that. So the next thing we want to take a look at is what's going on with the actual AGN activity. Because the whole idea between dual and offset is based on how luminous they are. So here, we're looking at the Eddington fraction. And so the black line is, sorry, I'll put this on. So black line is before their first paracenter, and then blue, dark green, light green. So if you look at the primary black hole, as it goes through first, second, third paracenter, they tend to get brighter. If you look at the secondary in a dual case, it actually tends to get brighter and then get a bit fainter. On the other hand, if you look at the offset case, you see a very big change. After second paracenter, the offset tends to get much less active. Now, this is partly by definition because these are offset AGN, where we're defining one of them as not being bright. But again, we're seeing this is because of the stripping that really prevents these black holes from growing. So next, I just want to throw up one plot very quickly. I don't have time to really go through details of this, but just to point out another observational comparison. So here, this is looking at the luminosity of duals and offsets as a function of separation distance. And there's a fair bit we can unpack here, but really I just want to take a look. You can notice it's relatively small here as the absolute luminosity, but around 10 kiloparsec separation, we're seeing a bit of an increase in the typical luminosity. And this is matched with observational data that's finding an increase in AGN activity at approximately that distance. So this is because we have these incoming pairs that pass by each other and trigger each other based on this gas strip. So last minute or so, I'm going to go through something, just the last thing I said I would get back to, which is the actual merger rates and consider gravitational waves. So given these simulations modeling the infall of the black holes and the actual time frame it takes to merge, we can get a lot of information. So this is coming back to a similar plot to the first one I showed. So these three lines, the blue, sort of orange, yellow, and purple, are TNG 300, 150. And this is, again, the rate at which we would detect gravitational waves would reach the Earth from these mergers. And if you compare that to Astrid, there are a lot more mergers in Astrid, which seems odd given that the dynamical friction slows it down, but this is just mass dependent. So remember, I commented on the low mass that Astrid seeds black holes with. So this is just because there are a lot more seeded black holes in Astrid. If we limit it to just the mass scale that TNG 300 has, you can actually see Astrid has a lower merger rate than the TNG simulation. That's because the dynamical friction slows down the merger. But it's really important to do all of this because this is the set of all the mergers in TNG 300, color-coded by signal-to-noise ratio for LISA. And what you can see is really the very lowest mass resolved in TNG 300 is the peak of LISA's sensitivity. Whereas if you push to lower mass, then you start to really resolve the peak sensitivity and get to some with lower signal. And this ties in with the importance of the dynamical friction to really model the rates at which they're happening, because that's what causes this kind of shift. It's just including those rates. So there's a lot more work to do with these gravitational waves. So Tirta is one of the undergrads I'd mentioned. He's working on some of this to figure out more specific details on how adding spin contributions can affect it. But that's all I have time for here. So I will leave this up. Key idea is it's really important to model the dynamical friction, and once you do, you can get a lot of information in black hole dynamics and what's going on with black hole pairs as they're approaching each other. So thank you.
Okay, we have some questions here. Let me start here.
Thanks for the very nice talk. Hi, I'm Kaustav from Yale. So when two black holes, let's say 10 to the power 8 or something, solar mass black holes are pretty close to each other and, going around in circles, but are still, at a distance where it needs more dynamical friction to bring them closer before you call them merged. There, its rate of bringing them together very much depends on the local density of stars and dark matter and gas and everything. And on the other hand, the local density of stars and dark matter very much depends on the interaction with the black hole, because it's expected that they will, throw stars and dark matter away. How do you model that?
So the thing to remember is this simulation is a very large volume simulation, so it's still quite limited in resolution. So let's see if I can do all this. So we are using sort of an analytic estimate for what the dynamical friction should be at resolutions below what we can resolve in the simulation. So yes, it's not going to be perfect, but it's at least a drastic step above just saying, move the black hole to the center of the galaxy. And then this kind of thing can also be applied to higher resolution simulations. And so you can do it even if you're not doing as large volumes, and then you start resolving these scales.
Okay, so just for the recording, so please maybe state your name before you ask the question.
Hi, Colin, thanks. Nir Mandelker, Hebrew University. Could you say again how you do the seeding? Like, is the seeding based on halo mass or gas properties, or? I'm trying to basically compare to the way they do it in the Romulus simulations.
Yeah. So the seeding just it's a halo criteria. So you need a halo mass above 5 times 10 to the 9, and it has to have a stellar mass above 2 times 10 to the 6. And if you have a halo that satisfies those two criteria, and it doesn't already have a black hole in it, one is put in. And then it is chosen from that mass range. It's a power law model with exponential. Really what you're seeing here. So it is entirely the halo property, and it's not looking at local behavior in a specific area inside the halo. That's it. Yes, but note the halo threshold in which we seed is also low. So it's not like we have, I don't have, I might have it in extra slides, I don't think I do, but yeah, okay. So ignore the colored dots here and everything, but you can see the black hole stellar mass relation. This is specifically looking at the dual and offset, so it's limited to above 10 to the 7. But if you look at the similar plot that extends to lower masses, it does continue down, and it's simply seeding in smaller halos than philosopherus and TNG do.
Okay. Okay. Yeah. Thanks, Colin. Hong Zhang from University of Arizona here. So I have one question and one comment. So the question is, in the slides you show two specific examples of how the secondary black hole grows relative to the primary black hole growth in the two of the galaxy mergers. So I was wondering if you have ever looked at how statistically secondary black holes grow relative to the primary black holes, because that could have significant implication on how we can interpret or like compare the simulations with the latest nanograph detection, because whether secondary black holes grow by a lot would affect the gravitational wave strains that we detect below redshift 2. And the comment is that for the gravitational wave or merger rates from Illustris or TNG, I think there's been some work on using similar like post-processing schemes on Illustris or TNG by Luke Zoltan, Kelly et al. And I think it might be a fairer comparison to compare with their results instead of just comparing directly with results with like no dynamical friction and no repositioning. Yeah.
Yes. I'm going to try and be quick because I think we need to move on. But I think I would argue that they're both fair. So when doing a comparison to show the importance of including the dynamical friction, it shows what the simulation is actually doing. Because you're now talking about post-processing, consider essentially changing what the masses would be. I've done papers doing that. It's an interesting and useful topic. But it also means you're saying the black hole should have had a different mass, which would have had a different effect on the galaxy, and the feedback would have been different. And so you sort of have a whole chain of later effects. But yes, there is a fair bit to look at here. I've been focused on just the separation between dual and offset here, but there's a lot to look at of just primary versus secondary.
Okay, thanks, Colin.